Hello everyone, hope you guys are doing really good. So today we are going to discuss differential kinematics, and in this scenario we are going to cover part 2 of our discussion. Remember, in the last lecture we have discussed the velocity kinematics, and especially the case was forward velocity kinematics. And in that, if I make you recall, we initially discussed the tools necessary to construct the Jacobian, and in that we have discussed all the different details corresponding to skew-symmetric matrices and how we're going to make use of those to construct the angular velocities and all that. But later on, we found out a very good way to identify the Jacobian, which relates the joint velocities with the end effective velocities. And we can now readily identify whenever we have a robotic manipulator in front of us, we can see what is happening with the arm and how the spherical wrist is constructed, or a wrist configuration is structured, and we can readily identify the Jacobian corresponding to it. But once the Jacobian has been constructed, we still have to identify certain aspects, especially whether we are going to achieve singular configuration or not. And that is generally the main focus in today's lecture. We are going to discuss singularities, and then in the later section we are going to discuss when you have a non-square Jacobian matrices, especially in case of redundant manipulators, how to handle that. So let's start the discussion. In the start, we should ask this question, that what is singularity? Or for robotic manipulators, what configuration be termed as a singular configuration? So the answer is that a configuration for which the rank of Jacobian decreases is called a singular configuration. Now at this particular stage, I should ask you to recall that last time we defined this configuration Q to be a vector having n variables in it, Q1, Q2, all the way to Qn. And actually this corresponds to n-link manipulator, which we define schematically to be something like this. It is just like a schematic. So this is the tool center point. So you have all these joints which are going to be Q1, Q2, all the way to Qn. So which means that a robot can be defined in terms of Qs, and that would be the configuration. So a configuration for which the rank of Jacobian turns out to be not full, that is the situation where you say that you have that configuration labeled as singular configuration. And you can recall that this rank was computed whenever the determinant of Jacobian, or any matrix for that matter, is going to become instantaneously equal to 0. And remember, these Qs are changing because the joints are moving, so you are going to have all these variables updating their values whenever the robot is in motion. So there is going to be some particular instances for which the determinant turns out to be equal to 0, and that indicates that the rank is no longer full, which means the configuration at that instance is a singular configuration. Singularities may manifest themselves at different places and in different ways. For example, singularities may represent configurations from where certain directions of motion may not be attainable. You would see that in one example later on. At singularities, bounded end effective velocities may correspond to unbounded joint velocities. What it means, like you have seen this expression x dot to be equal to Jacobian times q dots. So you have end effector over here at this site, and you have joint on this side. So what it means that if end effector velocities are bounded at singular configurations, when Jacobian reduces its rank, you are going to come up with unbounded joint velocities at singularity. So since we have seen the relationship between velocities of end effector and the joints, Jacobian is a very interesting piece of mathematical expression, which is also going to correlate the joint torques and the end effector forces. So similarly, the way we have defined this expression for velocities, you are going to find out at singularities, bounded end effector forces are going to correlate with unbounded joint torques. Moreover, at singularities, you would observe that the singular configurations are going to correspond to those points on the boundary of the workspace which are at the maximum reach of the manipulator. What it means, like for example, if I just ask you to consider a two-link manipulator, as we have seen in so many different cases. So if it is in this form where you have the bent elbow, you can find out, or you can draw this kind of profile. But if on the other side the same manipulator is fully stretched, let it be like using the same dimensions. If it is fully stretched, you can only have the possibility of drawing in a circular arc, which means that at this particular maximum stretched configuration, you would not be able to draw this kind of profile, which means obviously that you're going to reduce some flexibility or some degree of freedom when the arm is fully stretched, as is indicated over here. You will see that example later on, by the way. Moving on, singularities are going to correspond to points in the manipulator workspace that may be unreachable under small perturbations of parameters, for example, link lengths and offsets. And similarly, not only singularities are going to be important, but near singularities are also going to be problemsome, because you are going to find out mathematically, in case of inverse kinematics problems, that you have got multiple solutions on there. And for that reason, it is going to be a little bit of problem. So all the different singularities that we mentioned in previous two slides may be observed in this one video. In here, you would observe that there is one industrial grade manipulator which is experiencing singular configurations at multiple different places and at different times. So let's just observe what is happening in here. As we know that end effector velocities are equal to Jacobian times the joint velocities, we can take very small variations, and this would transform this expression into this expression, which means that there is a linear transformation between the two sides. The side which corresponds to the joint space over here, and the side which corresponds to the end effector space. This Jacobian is going to define how things are related with each other linearly in both sides. So in terms of one example, this can be well understood. Let's have this as the expression. Now in there, you can see that this matrix is the Jacobian matrix. And if I observe the values, these are two columns of 1, 0 each. What does that mean? I can suspect that there is going to be linear dependency of one column over the other. And for that matter, the rank of this Jacobian is going to be less than full. And this would mean that this dq is going to have not full effect on dx. If I expand this expression, this would be these two equations. And you can well understand now that dq1 added with dq2 is going to have an effect on the x coordinate in the end effector space, but these two are not going to have any effect on the y coordinate, which is obviously because of the way the Jacobian is constructed instantaneously over here. Because the rank is not full, because the determinant is going to be equal to 0, this would mean that the happenings on the joint space is not going to be fully reflected in the end effector space, and that is the manifestation of having a singular configuration. So in terms of statement, this can be like this, that the rank of Jacobian in this case is 1, and that's why dq1 and dq2 are not going to have any change reflected on the variable d phi, and that's why you have a manifestation of Jacobian in terms of unattainable direction of instantaneous motion. Alright, we have understood that the singularities are needed to be identified and analyzed as well, but how we are going to do that mathematically? Maybe we can use the principle of kinematic decoupling that we introduced while discussing the inverse kinematics. Yes, we can, but how are we going to do that? Let's observe. So suppose we have, in our case, a robot with n to be equal to 6, which means that you have 6 degrees of freedom robot. Now in this robot, using the concept of kinematic decoupling, we can say that you have two distinct parts in it. One, what we call an arm, and the second, what we're going to call a wrist. Now this arm is going to have any configuration. It can be RRR or RPR or any other permutation of that. And wrist, however, is a spherical wrist. Now, in that sense, you have 3 degrees of freedom coming in from the arm side and 3 more degrees of freedom coming in from the spherical wrist. Now, as we know that Jacobian is dependent on Q's, and for that reason, I can say that this whole big matrix, using this concept of kinematic decoupling, can be decoupled into 2 parts. One coming in from the arm side, which is responsible for attaining a position. That's why this subscript P is written there, JP, and the other one, which corresponds to have a specific orientation because of the spherical wrist. So you can say that you can have this virtual line, dashed line, subdividing the big matrix Jacobian into 2 sub-Jacobian matrices. And also you can recall that when we did compute this Jacobian, we said that there is this possibility of subdividing the linear velocity part of the Jacobian and the angular velocity part of the Jacobian. So this was the horizontal decoupling, if I may say that, and combining the two concepts together, I can have a grid of 4 sub-Jacobian matrices, something like this division and this division. I can call this to be J11, J12, J21, and J22. Now if I just take a different color over there and identify what kind of Jacobian it is going to come from the arm side, and this is going to correlate with the linear velocity side. And for example, J22, for example, is going to be coming in from the wrist side, and this corresponds with the angular velocity. Now with this realization that you have got the Jacobian constructed in 4 sub-Jacobians as indicated over here, J11, J12, J21, and J22. Now if I take this Jacobian once again and rewrite that, this is what we have decided: J11, J12, J21, and J22. So I'm going to take this J12 separately and try to write that one down. This is going to be like J12 is equal to Z3 cross-produced with O6 minus O3, the first column. The second column is going to be Z4 cross-produced with O6 minus O4, and the third column is going to be Z5 cross with O6 minus O5. We have already computed it in our previous lecture. Now at this particular stage, because it is a spherical wrist, which means that all these origins are at the same point. So this O3 is equal to O4 is equal to O5 is equal to O6. This would mean that this difference is going to become equal to a vector of zeros. So this is also going to be equal to 0, and this is also going to be equal to 0. And with this realization that you have got a cross product with this 0 vector, this would mean that the J12 is equal to 0, 0, and 0. And by the way, this 0 is a vector of 3 zeros in it, because the size of this is 3 rows and 3 columns. Now with this realization that now you have got J12 to be like structured 3 columns of zeros in them. So that would mean that if you now take the determinant of this big Jacobian, this would be equal to determinant of J11 multiplied with determinant of J22 on the diagonals minus determinant of J12 multiplied with determinant of J21. Now since J12 is a vector of all zeros, so determinant is going to become equal to 0. So that would mean that determinant of J is going to be equal to determinant of J11 multiplied with determinant of J22, and that's the expression if spherical wrist is used. What does that mean? It means that for singular configuration, this determinant of J is going to be equal to 0, and that would mean that either determinant of J11 is equal to 0 or determinant of J22 is going to become equal to 0. So these are the two possibilities. And interestingly, what does that mean? That whatever is going to be the determinant of J21, that is going to be immaterial in our case. So coming back to these two expressions, this determinant of J11 was for the arm. If you recall, in the last slide we did that, and this corresponds to the linear velocity. So either you're going to experience a singularity coming in from the arm and from the linear velocity component, or you're going to receive, because of this determinant J22 to be equal to 0, which is going to come from wrist, and because of the angular velocity. Sorry, the space is a little bit constrained. So with this realization that you have got for singular configuration, the two possibilities we're going to explore further. So I'll take wrist singularity first, and that is when you have J22 to be defined in terms of three vectors, which is Z3, Z4, and Z5. And for singularity, determinant of J22 turns out to be equal to 0. Now, if you have a 3 by 3 matrix and the determinant turns out to be equal to 0, it means that the columns, or for that matter rows, are going to be linearly dependent on each other. So this with this and this are somewhat dependent. And that is going to reduce the rank of the matrix. That is going to in turn manifest in terms of having a determinant to be equal to 0. Now, this is an important realization over here, that how you're going to map from the mathematical representation to the physical interpretation. And that is something like, consider this scenario. In this case, you can see the spherical wrist. And spherical wrist, you can recall, was having 3 joints in it, starting from axis Z3, Z4, and Z5. And at one instance, you can see that this is the situation where you have Z3 to be in line with Z5. Now, if that's the scenario, if Z3, in other words, and Z5 are collinear, then obviously you can see the physical meaning of saying that columns of the Jacobian are going to be linearly dependent. Or in other words, in terms of its physical meaning, if theta 4 is having a counterclockwise rotation like this, and theta 6 is going to have a clockwise rotation like this, forget about this direction, and this is happening in the clockwise direction, and these two velocities are happening exactly with the same magnitude, you are not going to have any movement exhibited at the end effector, at the tool center point. So this would remain stationary if that's the scenario. And that would mean that even if you have q dots moving, you don't have x dot experienced. And that is because the Jacobian in that configuration turns out to be singular because of this J22 to be equal to 0. But the question is that how we can prevent it, and that's the big question. So prevention can be done if you place mechanical limits on the wrist. So that can be one possibility. That would mean that you would not allow this collinearity to happen when Z3 becomes collinear with Z5. And similarly, you can add certain link offsets or twists in them so that this situation does not appear. So that is the possibility of preventing it. So rest singularity has been taken care of. We still have to see what is this arm singularity. And for that, we have to see that what kind of robotic manipulator we would like to use. So let's, in this particular example, take an elbow manipulator, which is an articulating configuration robot, something like this. You can see in this case, you've got a revolute joint as the first joint, you have another revolute joint, and you have the third revolute joint. So this is an R configuration. So when we computed the Jacobian matrices, we took into account the configuration of the robot, and that was used to compute the Jacobian matrices. So when we take this Jacobian into account, all the computations are done, you would find out that the J11, which we are interested in, by the way, because we have seen that the singularity may arise from determinant of J11 turning out to be equal to 0. So this is J11. So when you take the determinant of this, this would mean that eventually you will get some expression like this. Determinant of J11 to be equal to something like A2 multiplied with A3, which are the two link lengths, multiplied with sine of theta 3, and then you have multiplied with that A2 cos of theta 2 added with A3 cos of theta 2 plus theta 3, something like that. So this is going to be the determinant of this Jacobian J11, and where I can label, like, you have this as A2 and this as A3, and sine and cosines are corresponding to the thetas. So when you have a singular configuration, determinant of J11 would be equal to 0, which means that you have two possibilities. Either you have the first set of expression to be equal to 0. So this would mean that A2 multiplied with A3, then you have sine of theta 3 to be equal to 0, and then you have A2 cos of theta 2 plus A3 cos of theta 2 plus theta 3 to be equal to 0. In this particular case, you can see that A2 and A3 cannot be equal to 0, so the only possibility is that sine of theta 3 turns out to be equal to 0, and that would mean that theta 3 is either you have 0 or you have pi to be the possibilities. So these are the two possibilities of having a singularity arised from the configuration of the arm, and similarly for the other possibility, when you have A2 cos of theta 2 plus A3 cos of theta 2 plus theta 3, that would mean that you have some physical meaning, some physical scenario where singularity is going to appear. So in case of first possibility, where sine of theta 3 turns out to be equal to 0, as we've mentioned in the previous slide, you have these as the two possibilities. The first possibility in its physical realization appears to be like this. So you can see that when arm is fully stretched, and that was the point that we made earlier as well, that the singularities may appear at instances where the arm is in a stretched configuration, and that would turn this arm into losing some degree of freedom. So that is being exhibited over here. And the other possibility, when theta 3 is equal to pi or 180 degrees, this is going to indicate the physical setup to be like this. So we have said earlier that how to prevent these scenarios. So there is a possibility that you can place once again mechanical limits. You would not allow your robot to achieve those configurations which are going to be singular configurations. The other possibility is to have some algorithm which checks the instances where you have near singularities. So you can use those. The other possibility where you have a2 cos of theta 2 plus a3 cos of theta 2 plus theta 3 to be equal to 0. This was the scenario that we already covered while discussing the inverse kinematics. And remember, we said something about taking the top view from this side and observing where this point of intersection is, and when it crosses the z0 axis, you have that scenario where where r turns out to be equal to 0. And that was prevented as well in the previous discussions, and that was when we added an offset on the shoulder, in this case, like this, as is indicated over here in terms of d. So when you add this offset, obviously you may avoid that. So this is the prevention scenario, and this is the physical meaning of this expression. Let's have another example. That is of spherical manipulator. In a particular configuration, the spherical manipulator is parked over here, and you can observe that the z0 axis is passing through the point of intersection. Now, if you add a spherical wrist onto this point of intersection, any movement on the spherical wrist, when combined with rotations about the base, is going to render the tool center point to not move. And for that reason, this configuration can be termed as a singular configuration. Another example can be of SCARA manipulator. Remember, SCARA stands for Selective Compliance Assembly Robotic Arm, and it is a 4 degrees of freedom robot. And the first 3 degrees of freedom correspond to the arm, whereas the last one corresponds to the wrist. So at this particular stage, we will just focus on the arm, because arm singularities are being discussed. So that part of the Jacobian is going to be J11 and is structured to be like this. Whereas these alphas are symbolic representations which are going to have actually these expressions. I should make a point over here that there is a typo in the book. Please make a correction. This is A2. This is also A2. Please make this correction. Now, coming back to the point, the determinant of J11, when this turns out to be equal to 0, you are going to have a singular configuration. So this determinant in this particular scenario is going to be minus alpha 1 alpha 4 plus alpha 3 alpha 2. And you can plug in these values in there, and once you do that, it would mean that actually, before I do that, I'll write this one down, that alpha 1 alpha 4 should be equal to, in that scenario, to be equal to alpha 2 alpha 3 at singular configuration. Now it means that now you can plug in those values, and that would be equal to minus a1 sine of theta 1 minus a2 sine of theta 1 plus theta 2 multiplied with alpha 4, which is a2 cos of theta 1 plus theta 2, to be equal to a alpha 2, which is a1 cos of theta 1 plus a2 cos of theta 1 plus theta 2 multiplied with alpha 3, which is minus a2 sine of theta 1 plus theta 2. If you expand it, it would mean that you have minus a1 a2 sine of theta 1 cos of theta 1 plus theta 2, and then you have minus a2 squared sine of theta 1 plus theta 2 cos of theta 1 plus theta 2 plus a1 a2 cos of theta 1 sine of theta 1 plus theta 2 added with a2 squared cos of theta 1 plus theta 2, and you have sine of theta 1 plus theta 2 to be equal to 0, and this cancels this one, and that would mean that you have got the remaining expression. And if you expand it further, you would observe that eventually this turns out to be, in a sense, that you only have got sine of theta 2 to be equal to 0, and that would mean that you've got theta 2 to be equal to 0, or it is going to be equal to pi. So in terms of its physical realization, the situation would look something like this. And you can see that this is the situation corresponding to theta 2 to be equal to 0. And this means that the arm is fully stretched. And we have discussed this thing earlier, that when this happens, the arm loses 1 degree of freedom at least. And that's why it is singular. Now the other situation, when theta 2 is equal to 180 degrees, is mechanically prevented. You would not allow this robot to go there. So far, we have only discussed forward velocity kinematics. And the expression is this. And on this side, on the left-hand side, you have the end effector. And on the right-hand side, you have the joint or joints. So the joint velocities, if they are being acquired using some sensors attached to the joints, when combined with the Jacobian information that you're going to construct once for all, you are going to find out how your end effector is behaving in terms of its velocities. But this is only the forward velocity kinematics. Remember, at the same time, we need to solve the inverse case as well. Inverse velocity kinematics would mean that you would wish to find out those reference signals given to your motors, which are going to govern the motors to behave in a specific fashion. In this case, having specific speeds. So that would be something like inverse problem, in a sense that Q dots are needed to be known when you have the information about the end effector velocities, and that would construct something like this. Obviously, Q dots are indicated on the left hand side, and you are going to use the desired end effector velocities on the other side, but then you need to take the inverse of Jacobian. Now, I need to make you recall that Jacobian, when taken the inverse of, it is going to be equal to adjoint of Jacobian divided by the determinant of Jacobian. Now, the singularity discussion that we have had is also going to become significant over here, because whenever the rank reduces to a specific value, to a lower value, it is going to make this determinant equal to 0, and for that matter it is a divide by 0 situation. Now this is problem sum, obviously, and that would mean that in terms of its physical realization, the bounded end effector velocities may end up giving you unbounded joint velocities, and that was one of the definitions that we described in the very initial phase of this lecture. Cutting short, this expression that is written down over here is the expression for inverse velocity kinematics, and that you have to continuously solve all the times alongside the forward velocity kinematics. Now, in case of differential kinematics, velocity is not the only thing desired. You need to take another time derivative, and you need to acquire, for that matter, acceleration kinematics as well. So you would start from this expression that we have seen so many times today, and you're going to take another time derivative of it to acquire this expression. So this is the time rate of change of the first expression. So it contains obviously two components in it, and in this expression you have Q double dots, which are the joint accelerations. And obviously, as a result of adding these two factors together, you are going to get the end effector accelerations. Now, at this particular stage, I would say that I'm going to assume that B is equal to JQ Q double dots, and that would make this expression to be like this. What I've done, I've replaced this this expression with B, and I've taken the other component on the other side, and that would mean that B is equal to X double dot minus the other, on the other side you have taken this d by dt of Jacobian times Q dots as well. And that would mean that now if I just take the inverse problem, that would mean that you have got this as the final expression. Q double dot is going to be equal to Jacobian inverse of B, and that is an important expression in its own right, because this gives you the inverse acceleration kinematics. So if I just label them, you have these two expressions. This is the forward acceleration kinematics, and this is going to be, this whole expression is going to be the inverse acceleration kinematics. But in both of these expressions, you can see that we are taking the inverse of Jacobian. Now, obviously, singularity is an important aspect to be considered whenever the inverse is taken. So Jacobian inverse is actually, as we've already mentioned, that it is equal to adjoint of Jacobian over determinant of Jacobian. So all the discussion that we have already had in terms of detecting that whether the rank of J reduces or not is going to remain relevant. But the other issue is that generally what we have discussed in our earlier classes is that we are taking the inverse of a square matrix oftentimes. Now this means that if you have 6 degrees of freedom for your robot, then obviously the Jacobian is going to be 6 by 6, but it is not always the case. So this would mean that when you have n to be equal to 6, but what if n is not equal to 6? What is going to happen? So this is the situation which we need to still cater for. What if you have n to be less than 6 or more than 6? And that is where you have to consider a non-square Jacobian matrix. And that is the situation which we are going to handle in the next slide. Let's consider a particular scenario. And we're going to call this as a redundant manipulator for a specific reason that it has got more degrees of freedom than the required degrees of freedom. So consider the scenario where you have a planar robot and this planar robot has got 3 degrees of freedom in it. So this would look something like a modified version of the robots that we have, the planar robot that we have discussed so many times. So you've got one link like this, there is another link like that, and then you have another link like this. So in this particular scenario, you have 1 degree of freedom over here, another one, and another one. And that would mean that you have got the tool center point right over there. So in this particular scenario, you can obviously observe that in order to move or write anything on a plane, you need only 2 degrees of freedom, and obviously it has got 3 degrees of freedom, which is 1 more than required DF, which means that there is a degree of redundancy in it. And that's why we are calling these robots to be redundant manipulators, because they have got some more degrees of freedom than the required degrees of freedom. So if we consider finding out the expression, and if this is theta 1, and if this is theta 2, and this is theta 3, the expression is going to come up in terms of x and y to be like this: a1 cos of theta 1 plus a2 cos of theta 1 plus theta 2, and a3 cos of theta 1 plus theta 2 plus theta 3 as the first expression for the x coordinate. and for the y coordinate similarly you're going to construct the other expression. And that would mean that the Jacobian, if we wish to compute that, is going to come up like this. And in this scenario, you can obviously observe that it has got 2 rows in it, and it has got 3 columns in it. 1, 2, 3 columns in it. So it is a 2 by 3 matrix. Obviously, it is not square. So for that reason, taking the inverse of this Jacobian matrix is needed to be especially considered, because the conventional paradigm is not going to work for us. So on top of that, you've got 2 linear equations and 3 unknowns for that, and that is going to make this problem slightly different from the problems that we have discussed so far. So we're going to start from making a proposition. So this proposition is something like this, that you have got for Jacobian, which is sized m by n, in such a fashion that m is less than n, and also you are ensuring that the rank of j is equal to m, that for the lower dimension it is not singular. So if you have that scenario, then obviously Jacobian times Jacobian transpose inverse is possible. And I will explain it in this scenario, that if you have Jacobian, which is m by n sized, and if you multiply that with transpose of itself, so this is going to be n by m, which means that this whole matrix after multiplication is going to be m by m sized, which in a mathematical notation that we are adopting over here means that Jacobian transpose is going to be sized m by m. And now since you have rank to be equal to m, which means that we are not observing any singular configuration. So with this realization that you have got the possibility of JJ transposed inverse possible, now you can say that if you have any matrix, let's say A multiplied with A inverse, that is going to be equal to identity matrix. But now I'm going to replace this A with Jacobian transpose on this side, and Jacobian transpose inverse on the other side. So this is also going to be equal to identity, obviously. And if I just regroup it in a little interesting fashion, that would be something like I'm going to place a bracket over here and over here. So if I do that, this thing on the left hand side is a Jacobian, obviously, and the remaining stuff is Jacobian transposed multiplied with Jacobian transposed taken inverse of as well. That is equal to Jacobian, and I can place this thing in a different notation like this to be equal to identity. I'm going to use a different color to highlight this whole thing is what we call pseudo inverse. Actually, since it is on the right side, so it is called right pseudo inverse. You can find out a left pseudo inverse as well, but in this case we are just focusing on the right pseudo inverse. And this is going to be very handy whenever you have non-square Jacobian. and that is generally the case whenever you have redundant manipulators. And now when I use the word redundancy, it means that the manipulator or the robot has got more degrees of freedom than the required degrees of freedom for that task. Now at this particular stage, it can be easily demonstrated that a solution to x dot to be equal to Jacobian times q dot is going to be given by this expression q dot to be equal to right pseudo-inverse of the Jacobian times x dot plus you have I minus Jacobian pseudo-inverse of Jacobian times Jacobian into b. Now in this case, this b is an arbitrary vector. And this is going to be n dimensional. Now in this case, I should also emphasize that solution of this expression is going to be given by this equation. But how we're going to do that? How we're going to show it? That's the question. So let's do it like in a little intuitive way. So I'm going to multiply Jacobian on both the sides. So it is going to be jq dot on this side, and then you have Jacobian pseudo-inverse times x dot plus Jacobian multiplied on this side as well, I minus Jacobian pseudo-inverse times Jacobian into b. And then obviously Jacobian inverse or pseudo-inverse is equal to identity matrix. So this is going to be equal to x dot plus j minus j pseudo-inverse times j into b, and this is going to be equal to x dot plus j minus this thing, let me use a different color, is also going to be identity, so which means that you have j minus j in this side times b, and obviously this is going to be making you see x dot to be equal to Jacobian times q dot. Now what does that mean? It means that the vector b, which is an arbitrary vector, you can specify any vector corresponding to speed of the manipulator or speed of the joints, and that is going to give you the possibility or multiple possibilities for that redundant manipulator to achieve. And this is generally what we do whenever we have more degrees of freedom than the required degrees of freedom in order to have different possibilities of the solutions presented to us. In our own lab, where we are making one collaborative robot, which is 7 degrees of freedom robot, which is 1 more degree than the required degrees of freedom, we are using this vector b to identify any situation where we wish to find different solutions, where we wish to allow the robot to safely behave whenever there is a human worker in the proximity of it. So we are using this vector b to our benefit in order to identify the possible solutions which are going to greatly help us in making this whole activity to be a safe activity for redundant manipulators. So this is a very handy tool to have when you have possibility of selecting speeds arbitrarily using this vector b. This is it for today's discussion. Today we have covered in much more detail what is meant by singularities, and this is in continuation with the differential kinematics that we discussed in the previous lectures. So this discussion is not in isolation. This is very well connected with the previous discussions when we discussed the construction of Jacobian, and prior to that all the forward and inverse kinematics discussion that we have had. So this is in continuation with that. So please follow this lecture in connection with the previous discussions. And also I should once again re-emphasize that you need to solve the end chapter problems, and that is going to allow you to understand in much more detail how the singularities manifest themselves and what are different possibilities in them, and how you're going to analyze or how you're going to use the tools that we have discussed in this lecture to better understand the physical meaning of it. So if you have any queries related to this lecture, you can always post in the comments section, or you can also post your queries in the Teams folder that I've already shared. So see you next time.